Okay, sorry, I forgot to start the recording. So, this was the first page. So I recalled the inverse mapping theorem, and then we are trying to prove this closed graph theorem. So this says that if V and W are Banach spaces and T is a linear map from V to W such that graph of T is closed in V cross W, then T is continuous. That means that T is a bounded linear operator from V to W. So to prove this, we are taking defining a norm on V cross W by norm of x comma y is norm x plus norm y. So with respect to this norm, the topology on V cross W is same as the product topology of V cross W. And because V and W are Banach spaces, this Z becomes a Banach space with this norm. And now because graph of T is given to be closed in x cross y, this graph of T is closed subset of Z, this nonlinear space Z. And because Z is a Banach space, any closed subset with the norm restricted to that, that will be a Banach space. So G of T is a Banach space. So now, if we define map, define this projection map P from Z to V by P of any element of Z is of the form. No, let's define this from G of T to V. So now we are defining this for any point in G of T is x comma T of x. So P of x comma T of x is equal to x. We are just taking the projection on the first component. So P of x comma Tx is equal to x. Then what can we say about this map? Then P is linear is clear. So P is a linear transformation from G of T to V. Also, P is one and onto. Right? This is also clear. It is onto because for any x, you see that x is the image of x comma T of x. And 1 is again clear because if you have P of x1 Tx1 is equal to P of x2 Tx2, then that implies that x1 is equal to x2. So x1 Tx1 is same as x2 Tx2. So P is linear 1 onto, and also P is continuous. Also P is continuous. This is because if we look at norm of P of x comma T of x, this is same as norm of x, which is less than equal to norm x plus norm Tx, which is same as norm of x comma Tx. Right? Because this G of T is a subset of this Z, and on that the norm was defined as the x comma Tx. So P of x comma tx is less than equal to norm of x comma tx. So that means that P is a bounded linear operator. So this P is continuous. So now we'll use this inverse mapping theorem, because this G of T and V both are Banach spaces, and P is the bounded linear transformation, which is also 1, 1 and on 2. So by the inverse mapping theorem, P inverse will also be continuous. So by the inverse mapping theorem, P inverse from V to G of T is continuous. Now what we had to prove was we have to prove that T is continuous. So P inverse is the map which maps x to x comma t of x. So we know that the map x going to x comma t of x, that is continuous. And then if we compose that by the projection on this second component, then that is also continuous. So therefore the composition will be continuous. Or we can use this norm also. So if we look at norm of Tx, this is less than equal to norm x plus norm Tx. And what is norm x plus norm Tx? This is norm of x comma Tx. And x comma Tx is same as P inverse of x. So norm Tx is less than equal to norm of P inverse x. And we are given that P inverse is continuous. So this will be less than equal to norm of P inverse times norm x. So this implies that T is bounded and hence continuous. So again, you see that to prove this theorem, we are using this inverse mapping theorem, which was proved using the open mapping theorem. And to prove open mapping theorem, we need that bare category theorem. So basically, this graph closed graph theorem is again a consequence of bare category theorem. So in fact, it is important that this x and y are both Banach spaces. If either x or y is not complete, then we can get example where graph of t is closed but t is not continuous. So let us look at one corollary to this. So if we have two Banach spaces V and W, so if V and W are Banach spaces, and T from V to W is linear, then T is continuous if whenever if we have a sequence xn in V which converges to x naught, whenever xn converges to x naught in V and Txn converges to some y naught in W, we have y naught is equal to T of x naught. So in general, to prove continuity, we need that if xn converges to x naught, then T of xn should converge to T of x naught. But here we are saying that if this V and W are Banach spaces and T is linear, then uh, it is enough to show for xn converging to x naught and Txn converging to y naught is equal to Tx naught. So that means that here, I mean, we can assume that xn is a convergent sequence in V and Txn is also convergent, and then you just prove that this y naught is equal to T of x naught. So this is weaker than I mean, proving the continuity by just showing that xn converging to x naught, then Txn converges to Tx naught. So why is this? This follows by closed graph theorem because this condition implies that graph of T is closed. So if we have this, now we will just prove that graph of T is closed. So we will show that graph of T is closed, and then the result follows by the closed graph theorem. So to prove that graph of T is closed, So let some x comma y belongs to the closure of graph T, then there exists a sequence xn txn. This is in graph T such that xn comma txn, this converges to x comma y. But this implies xn converges to, let's write this as x naught y naught. So xn converges to x naught and txn converges to y naught. And now this implies, by the assumption, this will imply that y naught is equal to t of x naught, which implies x naught comma y naught belongs to graph of T. Therefore, graph of T is closed. So for a linear transformation between two Banach spaces, to prove continuity, you can assume that there is a sequence xn converging to x naught and txn converges to y naught, and then just prove that y naught is equal to t of x naught. That will imply that t is continuous or bounded operator. And in fact, I mean, you can also assume that xn converges to 0 and txn converges to some y naught, and then prove that y naught is equal to 0. Because if xn converges to x naught, then that implies that xn minus x naught converges to 0. And because t is linear, t of xn minus x naught is same as txn minus tx naught. So by this you see that you can even assume that this x naught is equal to 0, and you can do this.
So the statement of the corollary can be like equivalently stated to have that whenever xn approaches 0, then txn approaches 0. If this is true, then t will be continuous.
No, I mean that is always true for a linear operator. If xn approaches 0, and that implies that txn approaches 0, then t is continuous at 0, and then by linearity t will be continuous at any point, right? But what I am saying is that if we assume that xn approaches 0 and txn is just convergent, and then I prove that txn converges to 0. Right, so it is weaker condition that we are only assuming that txn is convergent, and then showing that that will imply that it is convergent to 0.
Okay.
Okay, so that is the main advantage of this corollary, that here we are assuming that xn is convergent and txn is also convergent, and then we are proving that whatever txn converges to, that is t of the limit of xn, right?
So usually we'll have to first show that txn is also convergent, and then we'll have to show that y naught is tx naught, or equivalently for the 0 case. But now we can already assume that
Exactly.
txn
We assume in advance that xn converges to some x naught and txn is converging to some y naught, and then just prove that y naught is equal to tx naught. In general, you will have to prove that if xn converges to x naught, then Txn must converge to Tx naught. So first of all, it should be convergent and it should converge to Tx naught, right? So there is a difference. Maybe I'll like give some problem where you will see how you can like apply this to prove continuity, and that will show you that it can become easier by assuming that Txn is already convergent. Okay, maybe in next I'll try to give example which shows that this X and Y, V and W being complete is actually so. I mean the theorem says that this VW being Banach spaces, that is like a sufficient condition, but it is also necessary condition. That means that we if V is not complete or W is not complete, then we have examples where this closed graph theorem is not true. So remark. The completeness of V and W in the closed graph theorem is necessary. So let's look at this example. Following examples. So the first one, let's look at this derivative operator. So we'll take let V equal to C101. So what is that? This is equal to all continuously differentiable function on 0, 1. So this is the collection of all f from 0, 1 to R such that f is differentiable and f prime is continuous. And what is the norm on this? Norm, we will just take the supremum norm. So with norm of f is equal to supremum of mod of f of t for t belonging to 0, 1. So because this C101 is a subset of C01, so we can take the norm which is on C01. So this is for all f in V. And note that there are other norms also on C101. I can take supremum of mod ft plus supremum of mod of f prime t. So with that norm, this V becomes a Banach space. But with this norm, this is not complete. Note that this V is not complete with the above norm. And let W is equal to C01 with the A sup norm again. So this is just the space of all continuous function, continuous real valued function on the closed interval 0, 1 with norm equal to supremum of mod ft. So now what we can do, we can define a linear transformation from V to W. So define T from V to W by T of F is equal to F prime, because we are taking the F in V, so that means that F prime is defined and F prime is continuous. So F prime will belong to W. So this is a well-defined map from V to W. And what can be about this map? So clearly T is linear by the linearity of derivative. We know that this is a linear transformation. Is it continuous?
No, because the f prime is not bounded.
Yeah, this map is not bounded, right? So because we can take say f of t is equal to t to the power n, and then t of that f will be equal to n times t to the n minus 1. So if you look at norm of that, it will be equal to n, but norm of f is equal to 1, right? So this is not bounded. So t is not continuous. This is because if we take fn t is equal to t to the n, then norm of fn, this is in V, this is equal to 1 for all n, but the norm of t of fn, this is norm of fn prime, and fn prime will be of t is t times n to the t n times t to the n minus 1. So this is equal to n. So this implies that t is not bounded. So this is a linear map which is not continuous, but we can see that graph of t is closed. So how do we see that graph of t is closed? In V cross W. So if we take any thing in the closure, So let Fn comma Fn prime. This is in graph T, right? Because Fn prime is T of Fn. So if this converges to some F comma G in V cross W, then we have to show that uh, F comma G belongs to graph of T, which means that G is equal to F prime. So we have to show F prime is equal to G. So why is this? So Fn prime converges to F G means Fn converges to F and Fn prime converges to G. So, and on V and W, we have this subnorm. So we have Fn minus F. This infinity norm. This goes to 0 and Fn prime minus G. This also goes to 0 as n goes to infinity. So therefore, this Fn prime, this converges to G uniformly on 0, 1. Right? Because this is the supremum norm, supremum of mod Fn prime T minus G of T, that goes to 0. So that is the same thing as the uniform convergence. So Fn prime converges uniformly to G, and if Fn prime converges to G, some function G uniformly, then integral of this will imply integral of Fn prime right Fn prime s ds from 0 to t. This converges to integral g of s 0 to t. Right, this is true for all t in 0, 1. But what is this? This is same as Fn of t minus Fn of 0. This is integral of 0 to t Fn prime s ds. This is by the fundamental theorem of calculus. So we know that this integral Fn prime, this converges to integral of g. And what do we know about Fn? Fn converges to f. So Fn of t will converge to f of t, and Fn of 0 will converge to f of 0. So for this side, this converges to f of t minus f of 0, and we know that integral of Fn prime, this converges to integral of g. So this will converge to integral of g. So this implies that f of t minus f of 0 is equal to integral this. So this f of t will be equal to f of 0 plus integral 0 to t gs ds. So if f of t is equal to this, the right hand side here we know oh, this is differentiable because this g is continuous, right? So this is differentiable. And what is the derivative of this right hand side? It's
dt.
just g of t, right? So oh, since the right hand side is differentiable, derivative is g of t, we get f prime t is equal to g of t. And this is what we had to prove, that f prime is equal to g. If we prove that, this implies that f comma g belongs to graph of t. So that means that graph is closed. So here you see that graph of t is closed and t is a linear map between two non-linear spaces, but t is not continuous. So here what fails is that the domain space V here is not complete. W is a Banach space, but V is here is not a Banach space, and therefore we cannot like expect that graph of T closed implies T is continuous. So this example shows that the completeness of V is the required for closed graph theorem. Second example,
So how did we show that V is not Banach? Like how did we show C101 is not Banach space?
you can show that this is not closed in C01
Right. Okay.
because this we are taking the same norm which is on C01, right? So
Right.
if it is complete, then it has to be a closed subset of this W, right?
Right. Right.
But you can easily see that this is not closed.
Right.
Right, because you can have a continuous map which is like uh, limit of a sequence of these differentiable functions in V. It's a okay. So I mean, now one way. I mean, you can say that if you understand this example, then this will imply that V cannot be complete, right? Because if it was complete, then by closed graph theorem, the closeness of graph should imply that T is continuous. But we are seeing directly that T is not continuous. So, I mean, one way is to use the closed graph theorem to say that this V is not Banach. But this you can directly also see that it is not Banach. Okay, so next, maybe let me explain why the completeness of W is also required. The completeness W is also necessary. So let's look at so let V be any separable infinite dimensional Banach space. So we are giving this for any separable infinite dimensional Banach space. For example, you can take say V is equal to say L1 or L2. So anything will do. So example, say V is equal to L2. So we take any separable infinite dimensional Banach space and take a Hamel basis for this. Let EI, I belonging to I, be a Hamel basis for V with, we can assume that all these EIs are unit vectors. We assume that norm of EI is equal to 1 for all I in I. Because if you take any basis and then you normalize it, we know that basis element vectors are all non-zero. So if you like write EI by norm EI, and then that will become norm 1 vectors. So we can always assume that the basis consists of only unit vectors. So if we take any Hamel basis, we have seen that if we have any infinite dimensional Banach space, then Hamel basis has to be uncountable, right? So since V is a Banach space, I must be, so also it is infinite dimensional. Infinite dimensional Banach space, I must be uncountable. Now we will define one more norm on this vector space V. So that also you have seen. So if we have any vector space, then we can define a norm on that by using a Hamel basis, right? So if we have any x in V, x is equal to summation of alpha I ei, I belonging to I, where this alpha I belongs to the scalar field R, and alpha I is 0 for all but finitely many i's. This is by the definition of basis, that any element can be written as a finite linear combination of the basis element. So x can be written as summation alpha ei, where alpha I is 0 for all but finitely many. So we can define a norm on this space. So define a new norm. Norm x1 is equal to summation of mod alpha I belonging to I. So even though I am writing this summation of mod alpha I in I, this is just a finite sum because we are only taking finitely many of these are non-zero. So this is a finite sum. So we define a new norm on this vector space V as this. Now let's define the identity map from V with the original norm which was given. So maybe here I'll write that some norm is given here with respect to which this was a Banach space, and then we have defined a new norm on that. So now define. So let W is equal to V with this new norm, norm 1, and define T from V to W by T of any x is equal to x. Right? So this is identity map, but we have different norms on the two spaces. Now what can you say about this T? So we claim that this T is not continuous and graph of T is closed. Okay, so if we look at norm of Tx, it is norm x1. Now let me define it from W to V. Then we can see that that is let's define this from W to V. Tx equal to x. So then norm of Tx. See, now Tx is in V, so we are taking the norm of Tx, and x is in W, so on W we are taking this norm 1. So norm of Tx is equal to norm x, and x is equal to summation of alpha I ei, where again this is just a finite sum, and this by triangle inequality is less than equal to summation I in I mod alpha I, because norm of ei is equal to 1. So this is just summation mod alpha I. And what is summation of mod alpha I? This is norm x1. So we see that norm of Tx is less than equal to norm x1. So this implies T is continuous. So T from W to V, this is a bounded linear transformation. So therefore, if we look at graph of this, graph of T is closed in W cross V. The graph of T, because for any continuous function, graph is always closed if we take it into any Hausdorff topological space. So graph of T is closed in W cross V. And this implies that if we look at graph of T inverse is a map from V to W. So graph of T inverse is closed in V cross W. So T inverse is a map from V to W, and graph of T inverse is closed in V cross W. So we saw that for this map T inverse, the conclusion of closed graph theorem is not true. So T inverse is a linear map whose graph is closed, but we claim that T inverse is not continuous. So why is that? T inverse from V to W, this is not continuous. So suppose T inverse is continuous, then T is a homeomorphism, right? Because T was continuous, and if T inverse is also continuous, then T becomes a homeomorphism from W to V. So that means that this norm space V and W, these are isomorphic, right? But what we know is that V is separable. However, this W cannot be separable. And T is a homeomorphism, since V is separable, we must have W is separable. However, if we look at norm of EI minus EJ on W, so on W we have one norm. What is norm of EI minus EJ? This is equal to 2 for all I not equal to j. Right? Because the way this is defined is you look at the summation of mod of alpha I. So here we have 1n minus 1. So the sum is of modulus of that is 2. So norm of ei minus ej is equal to 2 whenever I is not equal to j, and this collection ei is uncountable. So therefore it cannot be separable. This is the same reasoning that we showed that uh, L infinity is not separable. Same way here that you can see that this W is not separable, and therefore this T inverse cannot be continuous. So this shows that again here what happened was we have this T inverse was mapped from V to W. V is a Banach space, but W is not a Banach space, and graph of T inverse is closed, whereas T inverse is not continuous. Okay, I have already exceeded the time, so I'll stop here.